For this circuit, the DC analysis is going to be performed. To start, we're going to assume that the transistors are saturated. So we're going to assume this is saturated and this one is saturated. So that means that the currents into both of them is going to equal 0. So both of these currents are 0. And the other thing we know is that the current flowing in the drain also flows in the source. So these two are equal. And the same thing here. This current is going to be the same as this current. So this one has already given you a current of 2 milliamps. So this is 2 milliamps, which means that this one will also be 2 milliamps. So we're going to start with the solution for this current, which we don't know, and we can call it IS2 or ID2, either one. So they are equal. IS2 does equal ID2. So by setting these equal to each other, we also know the equation for a saturated transistor, which is this equation. So the next thing we need to do is find VGS2, and VGS2 is going to be VG2 minus VS2. And since we know the current going through here, we can take a loop and find VG2. So VG2, I'm going to take the loop. This would be a plus 10, and then a minus 2 milli times 3K, a plus 1, and then a plus 2, and then there's no current flow in here, so that's 0. So again, that was 10 minus 3K times ID1, plus 1, and plus 2. And ID1 was a 2 milli, so we get 7 volts for VG2. The next thing we need to do is write an equation for IS2, and IS2 is going to be a loop from ground to VS2. So this would be a minus 10 and then a plus of the current times 100, and then a plus 2, and this one is also a plus 100 times the current. And so again, minus 10 plus, and then a plus 2, and this just combined the 200s, so you have times 2. So here's our equation for IS2, and we now want to plug it into the IS2 equals ID2 equation. So the VGS2 is going to be plus 7, so we get plus 7 and then a negative of this whole quantity. So this term becomes a minus and this one becomes a plus. So there's a minus and plus. And then that simplified is 15 minus 200 IS2. And so we plug that into the IS2 equation. So here's our VGS2 minus VT, and VT was given as 2 volts in this problem. So we use that 2 volts. And then you can add the 15 minus 3 is 13 volts. And then multiplying that out, you get this. Remember to bring over this value to the other side so that you have it equal to 0. So plugging that in, this is our B term. So we use a minus B plus or minus the B squared minus 4AC. And in this case, this is our A and this is our C, all over 2 times A, which in that case is 4, so that becomes 8. So we get 2 values. And remember, this is a unique solution, so only one of these values is the correct value. So plugging in for VGS2, if we plug in, we need the quantity to be greater than 2 volts. And in this case, it's this answer of 11.5 milliamps is going to be the one that will satisfy this condition. The other one will be less than VT equal to 2 volts. So now we know the value of IS2, which also equals ID2, and that's going to be 11.5 milliamps. So now we can go back to the equation for VS2. VG2 we already found is 7 volts, and VS2 we can plug in that value for IS2, and that gives us a minus 5.7 volts. For the first transistor, we know that the current going through that is 2 milliamps because that's already specified, which also meant that it goes 2 milliamps here. So now we can plug in the equation for the ID equation for this one, and we know the Kn prime WL was given to us as 200 microamps per volt squared, and the 1/2 of that would be 100 microamps squared. VT is also given to us as the 2 volts. So then we can solve this. We can bring the 100 micro over to the other side by dividing it. And then we can take the square root of both sides. This square root with a square underneath will cancel out. And then we can bring the plus, or the VT over to the other side to be a plus VT, plus or minus the square root quantity. And that will be equal to VGS. So VGS1 is VG1 minus VS1. And VG1 we can find because we know the current in this branch here is going to be the same because there's no current flow into the transistor. So that's 0. So all of that current comes down here. And we can take a loop and we can start with the -5. So -5 is compared to ground. So the sign there would be a plus. So this is a minus. And then this becomes a plus. And then a minus of the 2 volts. So -5 plus 5K 1 milli. And then a -2. So that gives us -2, which we can plug back in for the VGS1. And so we get -2 minus a VS1. And then we can take the square root of both sides of this. And this squared underneath it gets rid of this side as square root. So this is plus or minus 20, square root of 20. And then we have -2 minus 2 is -4, and then a minus VS1. So this plus and minus is going to give us 2 answers. Again, the one we need is the one where VGS1 will be greater than VT. So in this case, it will be the plus square root of 20. And so that gives us a minus 8.47 volts for VS1. So the next thing we need to solve is to figure out if these transistors are indeed saturated, which was our original assumption. So we need to compare VGS2 to VT, and in this case it's a 7 for VG2, minus the minus 5.7, which was VS2, and that does equal 12.7, which is greater than 2, so therefore it is on. We also need VD2 to be greater than VG2 minus VT. So VG2 was 7 and VT is 2, so that has to be greater than 5. And the loop to find VD2, this goes from plus to minus, so it's going to be a minus 100 times the current, and then a plus 12. So that's where you have a minus and a plus. That gives us 10.85, which does indeed keep it in saturation because this value is greater than 5. This question also asked for the DC bias point for transistor 1. That is going to be either VGS2 or the current, and so we can just state that the bias point for this one is 2 milliamps. The last part of this problem gives you the actual AC amplification. So the AC amplification is a -6 volt per volt. And it says to also assume the input frequency is keeping it in the operating range and that the amplification does not pull it out of saturation. So we want to create a rough sketch of the total signal at VS2. And so from the analysis we found that VS2 in the DC was a -5.7. So we're going to take this value and multiply it by the input. And in this case it was 300 milli was the amplitude. And so we multiply it by 6. And so the maximum is going to be when we have a plus of this. So minus 5.7 plus this quantity gives us a minus 3.9. The minimum is going to be when we have a minus of that. So a minus 6 times the 300 milli amplitude. So that gives us a minus 7.5. So this is going to be centered around minus 5.7. And then it's going to go a high of minus 3.9 and a low of minus 7.5. This concludes this solution. Thanks for watching.